Entropy is a component of thermodynamics, and when it comes time to understanding entropy, there are 2 points of view we need to consider. The first and focus of this video will be what is the entropy of a molecule? What does it mean and how is it represented? In the next video, you'll find that entropy can be applied to reactions as well. So, what is entropy? Well, entropy is an expression of energy rearrangement during the course of a reaction. How can energy be expressed in a molecule? Well, there are a number of different ways. First off, there's rotational energy, that is, molecules spinning around an axis. Next, there are vibrational modes of entropy, that is, we have molecules with bonds, and these bonds can be stretching either symmetrically or asymmetrically. And finally, we can have the energy of movement from one point to another. These are all ways in which molecules can express energy. However, measuring entropy of a molecule is not exactly an easy thing to do. In fact, we can't measure the entropy of a molecule. So, how do we actually know the entropy of a molecule then? Well, we use something known as the Boltzmann's equation to determine what the entropy of a molecule is. Let's consider we have 2 atoms with a grand total of 3 quanta of energy to split between them. How many different ways can we distribute this energy? Well, between the 2 atoms, we have 8 possible ways in which the atoms can have energy expressed in them. So we call these microstates. Each one of the boxes to the right, that is the set of 2 boxes, is known as a microstate. A microstate is one possible outcome of many. And if you think about how big molecules can be, it becomes rather daunting to consider what the entropy could be within a molecule such as CO2, which has 3 atoms, and at 298 Kelvin, or 25 degrees Celsius, it has quite a few number of microstates available to it. But we can't measure it. It had to be calculated by figuring out the number of microstates. So, the entropy of a molecule is defined as being equal to a constant K, or Boltzmann's constant, times the log of the number of microstates. So you have to figure out how many possible ways a molecule can express itself in order to figure out entropy. Now, unlike enthalpy, delta H, entropy, delta S, is known on an absolute scale and was determined mathematically because there was no way of measuring it experimentally. Ludwig Boltzmann was able to come up with an equation to express the entropy of a molecule, and he was so proud of this achievement of figuring out what the entropy of molecules was, it was carved into his tombstone as seen below. However, in an ironic twist, log is what we now consider ln. And so the entropy a molecule has is equal to the Boltzmann's constant, Kb, which is 1.38 times 10 to the negative 23rd joules per Kelvin, times the natural log of the number of microstates. This provides us the entropy of a single molecule, that is S naught. In order to scale this up, however, to the world we live in, we multiply this entropy of a molecule by Avogadro's number, so we can find that entropy is measured in joules per mole Kelvin. So what does entropy tell us? Well, entropy tells us that the higher the entropy, that means the more ways a molecule has of expressing its energy. More motions equals greater entropy. And we'll expand on this idea in the next section as well, but first we need to cover the entropy of chemical reactions.